I will return to this evening's programme, and this is our annual Christmas lecture. I hope you've been able to partake of the mince pies before we started. But we are privileged this evening to have Professor Nigel Crook from Oxford Brookes University as our speaker. Nigel is the Associate Dean for Research and Knowledge Exchange and Professor of AI and Robotics. And he's the founding director of the Institute for Ethical AI at Oxford Brookes. And he's going to talk to us this evening on a topic which seems to have attracted considerable interest, backchat, generative AI, and the chatbots revolution. Over to you, Nigel. Thank you so much.
Thank you. Good to applaud at the beginning because you might not at the end. Thank you so much for inviting me here. Thank you to BCS Oxford for inviting me to give this lecture. I'm delighted to be here. It's a privilege to share this time with you. How long have I got, by the way?
Well, we normally say about 45 minutes and then have a good time for questions.
Okay, I shall try and honour that.
On people's minds.
I'll do my very best to honour that. So what I'm going to do this evening is kind of take you on a historical tour. I'm going to go back about 15 years and talk to you about what chatbots looked like and basically how they functioned 15 years ago. And then I'm going to take you through some of the progressions that have led to us where we are now with applications like ChatGPT. And then if there's time, and there may well not be, I'm going to sort of use that as an excuse to have a short rant about what we're doing in machine learning and the direction of travel and what I think we should be doing. Let's see how it goes. I have to log in first of all. Hang on a sec. Okay, so what I'm going to do is just going to play a short video for you of a chatbot that we developed here at Oxford as one of the partners of a European project, 15 partners, and the project was called Companions, EU funded. And the purpose of the project was to develop an animated avatar that you could have a kind of informal conversation with about your day at work. So you get home from your day at work, and you switch the avatar on, and then you have this conversation. And that's what you're going to see an example of next, hopefully.
Hello, John. How did your work day go today?
Worst day ever. I arrived late because of the traffic.
You have my sympathy. What happened next?
I missed the meeting on project responsibilities. I got more work dumped on me. Just what I don't need. I'm already likely to miss the deadline for a report.
I'm sorry to hear that. Who was at the meeting?
Only my team. They gave me a set of PowerPoint slides from the meeting. I spent the rest of the day reading the slides, but my computer crashed several times because of the updates.
Oh dear. It's understandable how you must be feeling. It's right to be unhappy about such a bad situation. Try not to worry about missing the deadline because of the technical problems. It's sad that your motivation could be affected by them. I can sympathize with your situation, but unfortunately the technical problems are unavoidable.
Wonderful, isn't she? Yes. So all the bits you laughed at were the parts that I worked on the project. So I don't take it personally anymore. But what I want to do is just to lift the lid on this a little bit and give you a feel for what actually went into creating that and making it do what we've just witnessed it doing. This system consisted of 17 separate programs developed by 15 partners spread across Europe and America. So it was a challenge in putting it together. And what I'll do is just kind of show you roughly how it was organized so that you can get an idea. so that when the user spoke into the microphone, what would happen is there was a group of modules that would process the actual signal from the microphone itself. There's speech to text, ASR, speech to text, which are actually Dragon. I don't know if anybody remembers Dragon, dictator, a huge dragon in this. And then other modules that are looking at the kind of the emotion of the user by the voice patterns, looking at the voice patterns. And that's all processed and then passed around to another set of modules with the text of what the system thought the user had said. And that's then processed by looking at what kind of things they were saying. Was it a statement or a question? That was then passed on to sentiment analysis, so looking at the text and what is the sentiment of the text. And then the sentiment was combined with the voice emotion to try and get sort of an understanding of where the user is coming from emotionally. Natural language understanding, doing a deep linguistic analysis of the text, so really understanding all the references and how they relate to each other. And that's all then passed to a dialogue manager that has the task of figuring out what to say next, basically. And that consults a user model, and that then hopefully, communicates to an effective module that kind of decides how the avatar will respond emotionally to that and help the user to respond. We get natural language generation as well, and that goes to a gesture manager that chooses what gestures to perform, and then that's passed on to the avatar, and it all happens. So that's why we had those long pauses. And the bits that you thought were funny was my task to try and fill that gap with back chat just on the basis of the emotional analysis of the voice, which was only 60% accurate. So quite often the user would say something and the emotion would be misclassified. You know, it'd say something like, I lost my job today. And you know, and she would come back and say, oh, good. You know, so she was unintentionally funny in that way. The bit that I did a bit more work on was in interruptions, because we had a thing about what happens if the user interrupts the avatar, especially when she's giving her long spiel, which could happen. How do we handle that? And we actually did a study on how people handle interruptions. We looked at the transcript of Any Questions, a Radio 4 program, and looked at different categories identified different categories of interruptions and coded all that up, and then we kind of built it into the system. And I'm just going to sort of show you roughly how it works now. So if the avatar starts speaking, there's a little module ATT at the top is told the avatar is speaking. And then if the user starts speaking, it could be that they're coughing, or it could be they're saying, yeah, it might actually be back channel, which is not an interruption, or it might actually be a proper interruption. And so that little ATT module makes that decision. The modules continue to process what the user is saying in the interruption. And then this little module decides, yes, this is a proper interruption, not just background noise or whatever, and informs the interruption manager, which was my module, which then told all the other modules in the system to pause. There's an interrupt happening. And then the avatar is paused, but we had to do it intelligently, so we didn't want it to stop halfway through a sentence. We wanted it to stop naturally so that it appeared human before allowing the user to continue with the interruption. And then you had to kind of repair the situation. So the whole system had to be aware that there's now some new text coming through from the user, and that has to be processed. The dialogue manager has to respond to it. And I'm just going to skip through these fairly quickly. And then that is output, and then the avatar will respond. So you can kind of see what's happening. There's an awful lot of processing going on. There's a lot of working out. All of this is based on a representation of what the user has said as text, converted into text and so on. And there is an intention behind this. So the dialogue manager had goals to communicate, goals to ask questions, find out what's happening, and that kind of drove the conversation. So just to give you sorry, this is not great visually, but this is a view showing some of the messages that are passing between the modules, and you can see the user says, hello, Sam, I've had a terrible day today, and it gets converted correctly in this instance, and annotated and all that. It's all being passed as text from one module to the next. That's how it was done back then, right? That's the olden days. This is ancient history in terms of AI, right? 15 years ago, 13 years ago. So what I want to do now is just take you on a tour of some of the technologies and developments that have led to where we are now with things like GPT. And so one of the original contributions was what is called bag of words. There's a famous quote here from John Rupert Firth, who's a linguist, who says, "You shall know a word by the company it keeps." So basically, the context of the word tells you what the word is about. So if I said to you, I went to the bank and cashed a check, probably something we don't do anymore, is it? Or if I said to you, I sat on the bank and fed the ducks, the context of bank in those two situations tells you exactly what the meaning of bank is, right? Or what I'm referring to. And that's what this means. You look at the context, you look at the words surrounding that. And different contexts, so in sort of, if you think about documents, have different groups of words they use, like sports documents and music. They'll all kind of have a vocabulary around which they use it. And we can use that to distinguish between them. One of the things that came early in that's relevant to what we're thinking about today is vector space models. And essentially what that is you look at a document as a whole, you count the number of times each word occurs within the document and across all the documents that you're looking at. You do some whiz-bang calculations. That is number of times a term appears in the document in proportion to the total number of terms in that document. And then inverse document frequency is the number of documents that you've got altogether in your set over the number of documents that contain that term that you're interested in. And what I've done here is just done a plot, imagining we have just plotting 3 words in our vocabulary. So these are on here, and the dots represent documents. When you've got that kind of situation, you can start to do some interesting things, because you can then say, well, actually, there's some groupings we can do. We can cluster these together now according to where they are in this space of words. And that you can then say, if a new document appears and it happens to be around here, then it's likely to be a science-based document. And you can make some inferences about that. Then around 2013, this concept of word embeddings came out. This is quite important. It's you kind of need to have a slight handle on this to be able to understand where we're going, direction of travel. And word2vec came out, which enabled the development of basically lists of numbers, which we call vectors, that represent the meanings of words in some sense. So I've shown here, this is a fabricated one, I just made this up. So imagine we just have 2 dimensions, and then what we have is the word, cow and pig are represented by these numbers here, 0.1, 0.2, 0.2, 0.1, and they're close together because they're related. They're farm animals and they're kind of close together, whereas car and love and hate are far apart in this space. And that's the basic concept of word vectors. The way this was developed, word2vec was, for those of you who understand neural networks, basically had a 2-layer neural network. They trained it on word associations, and then they took the weights from the network, and those were the vectors. So normally you would have lots more than just 2. You would have perhaps hundreds of numbers in your vector to try and capture all the nuances across different words. So now we come to language models. Hands up if you've heard of a language model. Quite a lot of people, yeah. It's out there, isn't it? There's people do have come across it. When I give these kind of talks, they know they've heard of it. They don't always know what it is. So let's just give a sort of fairly high level introduction. So actually, language models were originally developed in the early 1980s, believe it or not, been around for a long time. And the earliest kind of approaches used statistical methods to develop them using what they call word n-grams. So you kind of look at the statistical properties of words that are close together. So a bigram, a 2-gram would be 2 words consecutive in the text. You count how many times they occur, and a trigram, 3 words, and you just do some statistics on that. And that's kind of how they do that. But the kind of concept of a language model is that it estimates the probability of a sequence of words or tokens. That's what it does. Nothing more sophisticated than that. So if you gave it the sequence, the moon is made of cheese, it would return a high probability. And it's not a probability that it's true. It's a probability that it's a meaningful sequence of words. That's it, according to the data set that it's trained on. Right? If you take the same words and jumble them up, it's going to give you a low probability, because cheese of the is moon made doesn't really quite string together. Yeah, and the same happens with programming languages. Programming languages are generally just sequences of tokens, and it can learn to recognize meaningful sequences of programming language tokens and non-meaningful ones. And it can, you'll see later, it can generate sequences of those to create new computer programs. Okay, so the later models, large language models, started to use machine learning rather than sort of traditional statistical approaches, and used recurrent neural networks. If you know what those are, they have kind of feedback loops to be able to capture meanings of words across distances, and we'll come back to that in a second. And then the latest version of language models is that it has the power that we've seen in today's sort of applications are transformers. So 2017, there was a landmark paper that many people in AI would be aware of, created by people at Google, and the title was essentially "Attention is all you need." And what it's saying is this approach, this model solved a problem that had been faced by language models for many years, and that is what a language model tries to do is to try to learn the relationship between words in a sequence or tokens in a sequence. So we have quite an example here. So Emily in red and she, and the 2 she's, okay, we know when we read this that these words are connected. The model has to learn that. And the issue was for a long time that if the connections were too long for the model, it couldn't learn. So it would have a fixed window, and it couldn't learn relationships beyond that fixed window. What the transformer did was to scale that up and use what they call this a self-attention, which is attending to what this word means in connection to that word and to this word, and to do it very, very efficiently. So the original efforts with neural networks to do this used lots of recurrent connections, which were complex to learn, which meant they were slow and didn't work so well. The beauty of this algorithm is that it's just feed forward. It just goes in at one end, out at the other, which means that you can parallelize it, and you can put it on a huge compute farm, which is what they do at Google, and you can run it for several weeks to learn how to generate sequences of words and create a very powerful language model. Just to sort of give you an idea of what's going on here, the bit on the left is what's called the encoder. That encodes your input. So if that would be a query, if you write in, tell me a story about whatever, that would be the input. And then the bit on the right is called the decoder, which actually generates the output sequence that you see on the screen. Okay. And then we have these embeddings. So you remember the vectors that I talked about, that's exactly what these are, but they're word vectors. Each word has its own vector, which is fed in here. And the clever bit, I love this bit, is that there's a clever algorithm that figures out the position of each word in relation to every other word. And that's fed in and fed forward through the encoder. And then what you get on the outside, on the output of this, is essentially one of those spaces that I talked about, but immensely more effective than the word-to-vec approach that was used previously. Okay, so some facts for you, if you're into facts. So GPT 3.5 had an attention span of 4,000 words or tokens. So that's the width of the window that it could attend to. GPT-4 had 32,000 token wide attention span. So that is what makes the difference. And that is actually no theoretical limit. You just need a lot of compute power to be able to learn the model based on that. Okay. So then various bits of it have been used. So in 2018, this thing called BERT, bidirectional encoder representation from transformers, used essentially the left-hand side of that to create these representations, these long lists of numbers, these vectors that somehow contain the meaning of the input that you give to it. And that's very useful. We've used it on projects. So in 2019, we had an Innovate UK funded project where we were developing a contract negotiation tool with a local law firm. And the BERT model was used to classify the clauses. So you would read the clauses in, and it actually did a really good job. I mean, quite good accuracy in classifying the difference between, I don't know, I'm not a lawyer, a force majeure clause and, I don't know, limited liability clause or whatever it is. It could do that extremely well. And that turned out to be quite useful in the application they were developing for that. And then another one is Roberta. And Roberta does this sort of vector of numbers, but for sentences. So you can put in 2 sentences, say, it will figure out how similar they are by how far away they are from each other in this space. And this is what you're seeing here is a sort of classic linguistics conundrum. Time flies like an arrow. Anybody heard that phrase before? One. Yeah, not many. Oh, quite a few. Oh, good. All right. Time flies like an arrow. When I do this, people say, I've never heard that phrase before. Time flies like an arrow. Fruit flies like a banana. Okay. Now, the first 3 words are the same. So it's quite a hard problem to recognize that this is talking about little fruit flies, but like, different meaning of like bananas, and time flies like an arrow. And so you can kind of see that is a difficult problem. And here's some actual numbers for you. Here you can see the top sentence, and I've just put the first list. I mean, 1,024 numbers in this list, in this vector. So I've just put the first few in. Fruit flies like a banana. And then I asked Roberta to calculate how similar these are. It's using a cosine score. So a value close to 0 means that they're not similar. A value close to 1 means that they are similar. And you can see 0.3 is kind of close to 0. It recognizes that even though these 2 sentences use similar words, actually the meaning is quite different, which is, I was really impressed with that when I saw that. And then I gave it another sentence, fruit flies like a bullet. Right? So you can kind of see how close is is A to C. Fruit lies like an arrow, fruit lies like a bullet. 0.7. So it recognized that they actually have similar meanings, close to 1. Jolly useful if you can do that. Jolly useful. So now we come to the generative pre-trained transformer, GPT, which came out in 2018. And so what this does is it takes what we've just talked about, that language model, and it uses it to generate new text for you. So, for example, if you say, well, let's give it 3 words, once upon a, what would be the most likely next word to come out of that? And so what GPT does is, okay, it takes those 3 words, that sequence, and then it assigns a probability to every word in its dictionary, a jolly big dictionary. All right. And then what it does is it rolls a weighted dice according to those probabilities. Well, dice only has 6 sides, but you know what I mean. A weighted dice. This is called sampling in a statistical context, to choose the next word. So it doesn't always pick the very best next word, but it often picks a word that actually makes a lot of sense according to that probability. So do you see, even if you put the same query in twice, you get different answers because it's rolling a dice, a weighted dice, according to these probabilities. So how does it actually do it? Here's a high-level description of the process. So you give it the first word, that's input to that transformer, and then you get it. It rolls a dice, and upon is the next word that comes out with. So then you put that as input, and now you present both of those words, and it does the same thing again. It works out the probability of what the next word is across its vocabulary, rolls the dice, and then chooses the next word. That's it. That's what it does. That's what a generative pre-trained transformer does. If you understand that, you understand enough to know what's going on when you're using ChatGPT, mostly. So what I want to do now is just do a quick comparison of the good old days that I talked about at the beginning, pre-GPT chatbots, and where we are now, just to give you an idea of kind of how to interpret what's happening when you're using a GPT-based chatbot. And the first one is the architecture, so all the boxes that we looked at the beginning, in the pre-GPT chatbot, very handcrafted. Multi-modular, you saw the modules, all the different programs connected, sending messages to each other, handcrafted, multi-modular. The GPT approach, it might look complicated if you're not familiar with those diagrams. Actually, it's quite simple. It's one module, which is that, you repeat it, and you feed forward, and much simpler. In terms of development, the work we did originally was very handcrafted. We literally coded lines of code to generate behavior in the chatbot. In GPT, it's largely, if not almost entirely, machine learning. It's learned from data. What it generates is learned from data. The data sets we used originally, actually quite small. I mean, I was working on a data set that had about 1,000 statements. I thought it was brilliant. 1,000 statements is nowhere near enough, really, to do the kind of things that we do with modern language models. GPT used obviously massive data set, all of the text of the internet plus, and it's uncurated. When we chose our data sets, we chose them carefully because we knew what behavior we wanted. In GPT models, it uses everything, the good, the bad, and the ugly that's in the data that you can extract from the internet. Language understanding, again, we had experts on the team. Professor Sean Pullman, who was a group I was in at Oxford, expert in natural language processing, knew how language worked, knew how to code systems to understand and process language. All automated now, all automated. Meaning representation. You saw the messages that were being passed from the original demonstration I showed you. They were actually text messages. The hello, I had a terrible day was explicitly passed, so you could see, you could look at that and see what was happening. With GPT, no hope of looking inside it and understanding. You just get vectors of numbers, massive vectors of numbers being multiplied by other massive vectors of numbers. So the meaning is hidden, it's implicit, and it's distributed. Language generation, again, handcrafted and automated. Dialogue management, we had to actually explicitly manage dialogue in the original chatbot, all automated now. There's no management of dialogue. When ChatGPT chooses by rolling its weighted dice that the last thing, that this is the last word and there's a full stop is next, it stops. It's not managing a turn-based interaction with you or anything like that. It's automated. Output. Originally, so Samuela, the chatbot I showed you, was predictable pretty much. We knew more or less what she would say. She contained probably truthful information that she would say, sometimes get it wrong in a humorous way, but nothing particularly harmful. ChatGPT and all GPT-based are unpredictable. It's rolling a dice on data that it's trained that is uncurated, unpredictable. It's unbounded, and it has a tendency to hallucinate. Have you heard that term before? Yeah, he's telling lies. He's not telling lies because he's not telling anything. It's just, yeah. Conform to moral, social norms. Yeah, of course, we designed them originally to do that, not guaranteed with any GPT-based technology. Risk of harm, low. Originally, unknown, already caused harm. We know that GPT-based products have already caused harm in the world. Reach. So our model, our Samuela model, well, you needed about 3 or 4 computers to run it on your own network with people who are expert on how to connect these things together. So there was probably about 5 of us in the world that could actually run it. But ChatGPT, open to anybody who has an internet connection can use it. All right. So that's kind of my take on the comparison between the two. So I've just got a bit of time for a little rant on something that's related. So I want to give you some information. I hope this is correct information. Whenever I look this up, the figures seem to change. So the deep neural networks that we looked at, that architecture, the generative pre-trained transformer, GPT-3 had 175 billion weights. So the weights are the things that I'll show you in a second, but that connect the various decision-making units of the architecture together to get it to produce the right output. So 175 billion weights. GPT-4 had 1 trillion weights. Can you kind of even imagine what that might be like? The human brain has 600 trillion synapses, which is the equivalent. This is what these weights are representing, little synaptic connections. So you can see how we're not actually that far off in terms of numbers, what's going on in the human brain. But GPT-3, again, these are the figures that I've come across on the internet. Please correct me if I'm wrong. Used 1,287 megawatt hours over several weeks to train. The human brain, most people in this room, if you're still conscious, I think you are, using, about 20 watts. If I'm making you think hard, you're probably using about 20 watts of energy, which is 0.0002 megawatts. And we do that obviously over our lifetime as we learn a language. And I just thought it was fun to do some calculations. So 1 GPT hour of training, if you tried to sort of figure out how long would it take a human brain to use the amount of energy that GPT used to train for 1 hour, if I've done my calculations correct, it's 7,345 years. It's going to take a while, isn't it, right? And if you think, I think I've got the figure that GPT took 34 days to train. That turns out to be nearly 6 million years of a human brain. Now, a human brain can learn language, and I know all about sort of evolution and structure and all that kind of stuff. But this to me tells me we're doing something wrong. We're doing something wrong. And I think what we need to do is to look back at our understanding of how brains work, learn from neuroscience, and try and find better ways of doing this. And I'm going to try and persuade you of that right now. Before I do that, just to give you a insight into what's happening behind all of this architecture that we talked about, transformers are artificial neural networks that work like a brain, a little brain. We have, which is funny, there's a delay. There's a delay in the mouse, I won't use that. We have these circles represent brain cells, neurons effectively, and they're connected together. And all that happens is that you have some numbers on some of these cells that represent how excited they are. And then these are multiplied by these weights on connections that come into here. And then using that total weighted input, this unit decides how excited it's going to be. And how excited it's going to be is determined by a kind of function along here. So it's how far along here you move is how excited you're going to be, depending on your input, right? That's how neural networks work. And the algorithms, the key algorithms that are involved, figure out how to change these weights. So when you present a certain input, you'll get a certain output. All right, brains work differently. Neurons in brains work differently. You've got about 100 billion between your ears. And the cells are absolutely amazing. They have inputs. They have a kind of decision-making bit in the middle where the cell body is, and then they have an output, this is the axon. And what happens is that the decision-making decides whether or not it's going to pass on a signal, and the signal is like in the shape of a spike. This is the voltage inside the cell, which is resting low, below zero. If you hit the threshold, you get a sudden rush of the spike up, and then it comes down again. And this travels the whole length of that and is passed on to other cells through the synapses. So there's a whole area of computer science that looks at trying to model this and develop different ways of creating neural networks, and they're called spiking neural networks. They use this concept of a spike. And the reason why people are getting quite interested in this now is that the spiking networks tend to be, like the brain, much more efficient in terms of energy and computation than traditional artificial neural networks. So a neural network will pass inputs through all of its neurons and all of its connections, which is all right when you've got a little network like that. But when you've got trillions, you've got 1 trillion connections, that's a lot of processing, right? A spiking neural network, some of the neurons will fire and pass on signals, but not all of them. Yeah, much more efficient way of doing things. The problem with spiking neural networks is that they're harder to train, because learning in an artificial neural network depends on being able to figure out what the error is on the output. Yeah, so you calculate what it's producing and what the error is, and then you figure out how to change all the weights going back. Now, for computer scientists amongst you, you'll understand that means that we have to figure out which way to change the weight, to increase it or to decrease it, and it depends where your error is. Okay, and you compute that by calculating a derivative. Let's just put some equations there to keep some of the mathematicians happy. And that's what you have to do. You have to have a derivative. But the problem is with, and when you have that kind of Where's it? There it is. When you have this, you can calculate the slope of that at every point in spline, which is why it's used. Very powerful. But when you've got a spike, you know, we've got a 0, 1, there's no slope, right? And there are ways around it, but they don't work terribly well. They don't perform as well as artificial neural networks. I'm just trying to get back to where I was. So what happens is, the approach that's been taken is that you train your network. So you feed your inputs through to your outputs, and then you calculate your error and you change your weights so that you do better next time you see that pattern. And then when you've trained your artificial neural networks using a normal algorithm, the backpropagation algorithm, what you do is you copy those weights and you copy it across to a spiking network, and it works almost as well, very, very close to performance, but much more efficiently. And that's one of the common ways of doing that. I want to try and round off fairly soon, but I do want to share a piece of work that came out this year using spiking neural network technology. Small number of parameters, only 216 parameters, weights. It reduced the complexity of the self-attention bit of the transformer from quadratic to linear in the length of the sequence that you're processing, and is the length of the sequence. So it used a lot less energy, 20 times fewer operations. I think this is the future. I think this is the way we will need to go to bring down the cost and the energy uses of training these huge models. And then I think I probably ought to, am I nearing time, Andrew? 2 minutes left? 2 minutes, okay, 2 minutes. So 2 minutes for the final bit of the rant. So this way of looking at how neurons get excited is based on something called rate coding. So neurons communicate in different ways. They use different codes in the brain, communicating with each other. Some of them use like a machine gun effect, blah, 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 like that. And the speed in which the spikes come out is the rate value that's used, and that's what this approximates. No output, maximum rate output. It's a continuous scale. And that could be across an individual neuron, or it could be across a population of neurons. But the brain uses other ways of communicating. And one of the ones that's interesting to me is called temporal coding, where the timing of the spikes relative to each other are the carriers of information. Okay, so you can imagine like little sequences of spikes like this representing categories. And these two together, they're slightly different, but they basically represent one category. There's another category. Yeah. And so what's happening is that you have a much higher information carrying capacity here than you do with rate coding, much higher. Okay, that can be proven. But learning this is hard, because you're no longer just multiplying one number, which is your activation, times another number, which is your weight to get. Yeah. How do you do learning in this context? And that's what we've been working on at Oxford Brookes. The key thing that I think we're missing, this is the key trick, and if you're interested in sort of the computational side, this might interest you. So what we're doing in artificial neural networks is that the information content is structure-based. It's distributed across a huge structure of interconnected neurons, which makes it impossible to look at and understand. Whereas, if you used a signal-based, in other words, the information content is mainly in the signal that's passed, that makes for a much simpler and more efficient structure. The rate-based coding that we're using here is very good for modeling sensory signals. So like how much pressure you're feeling when you lift something, or how much heat, right? That's on a rate scale, or intensity of light in your retina, that's a rate scale. But what we've done is we've taken that simple way and tried to do everything with it. Right? And what I think is needed is that at some point we need to look at switching from information content that's in the structure predominantly to information content that is in the signal. Imagine if we invented computers like this, right? In a computer, we have information within the signal. You fetch and execute statements from memory and things like that. Okay, it's not structure-based, it's signal-based. And that's what I think we need to do, and that's the direction we need to move in. I'm going to skip over this bit, which is how we're proposing to do it for now, and just end on blatant advert for my book. If you're interested in the moral side of some of the stuff that I've talked about, then please do take a look at that. But otherwise, I think it's probably time for me to stop talking and allow time for questions.
Many thanks, Nigel, for the fascinating talk and a glimpse of some technology that's going to take us forward by the looks of it. We're happy to answer questions.
Yes,
just as a note, we'll take questions from the audience and from people online. If you're online on Zoom, please can you put your questions in using the Q&A tool in Zoom, and I will pick that up and pose the question to Nigel on your behalf. So I'm going to start with one question that we already have online, and this is from Andrew Beaumont, who says, how far in the future will it be that you can truly have a robot or computer with whom you can have an hour-long chat that is indistinguishable from that of an articulate graduate? Or will it never happen?
Gosh, that's a good question. And I am totally rubbish at doing these predictions. But I would say that it's perhaps sooner than many of us think. I mean, ChatGPT and that kind of development came sooner than I thought it would come. I thought we had to wait another, I don't know, 5-10 years or something like that. And here it is, performing remarkably well, actually, despite the fact that it's only producing probable sequences of words, and despite the fact that it's not actually trying to communicate with you. It's not trying to empathize with you. It's just generating highly probable sequences of words, but it does it extremely well. So I think probably not that far. I would hazard a guess that I could see that in the next 5 to 10 years.
And just to extend that point, then, what do you think drove? I mean, you made your estimates and you thought it would be a long time. What drove that improvement?
What led us to that sudden change? So I think two main things from my perspective. One is, well, the algorithm change, the algorithm efficiency of the transformer was obviously very key. That made it possible to train models that were performing extremely well. But in order to do that, you had to have massive compute capacity and a lot of money. I mean, it costs millions of dollars every time this thing is trained. It costs millions of dollars. And so you have to have corporates like Google and so on to be able to do that. And they took up the challenge and they did it. And this is where we are.
I applaud the idea of using the human brain as an inspiration for how to do things. But of course, humans learn with single trials. Which is very different to a backpropagation algorithm.
Yes.
So I wonder, do you need a completely different type of algorithm to a backpropagation?
Well, I mean, I guess you could argue that GPT type systems can do what they call few-shot learning, which is essentially you take the model as it is. It's got a basic capacity for language generation and that, and then you train it to do something specific on a relatively small number of cases. Or you might even just give it some examples, which you can do in ChatGPT. You can say, here's an example of answering this question. How would you answer that question, which is similar to it? So that is a kind of one-shot learning, but you're right. I think there's something else happening in the neuroscience that we're not catching on to that is much more efficient. We do know that humans and animals can do one-shot learning, very, very effectively. And I think we should be looking at how that happens. Yeah.
Relating, do you have to know GPT can be updated with a simple update? You have to rerun on
So I mean, I'm not au fait with exactly how they do it. I know that they only periodically do a complete retrain on the internet data. I don't know how often that is, but they can do this fine tuning. So you can take new data and you can kind of run the training on it on an existing trained model, and it can adapt to the new data. But every once in a while you just have to retrain from scratch. And I know actually I know someone who's sort of involved in training large language models, and they kind of figure out sometimes halfway through the training that there's a problem with the system, or they can't start again. It would cost too much, cost millions to restart it. So they have to fix the problem and then carry on. So the performance drops like this, and they say, oh, there's something wrong here. Let's figure out what it is, and they carry on from where they are, and it learns. Yeah.
Can I just check before we take another question from the audience? Are we hearing the questions online?
Not very clearly.
No. So
Use this, we will be able to.
okay, right. So next question from the audience is this gentleman here.
So on that subject, you can imagine a situation where, based on what I already know and so on, back in our ChatGPT, I have very firm ideas about how I would respond to certain things if I was asked, I would respond in a certain way. However, it might only take a few minutes conversation with somebody who perhaps teaches me how to differentiate, teaches me about some logic within algebra, which effectively lets me realize that if A equals B, then B equals C, and therefore A equals C, and so on. And all of a sudden, my entire future output will be radically different, because I will be able to, just with that bit of information, essentially, almost completely transform that previous training input. But it's hard to see how you can go from the current large language models to achieve that kind of transformation without, as you say, a massive retraining. So what could be the missing step?
So the two kind of angles to that. So one is that earlier versions, so GPT-3 in particular, 3.5, struggled with doing mathematical operations on large numbers. So if you asked it to multiply 1,733 by 2,700, blah, blah, it probably would get it wrong, because that data occurs probably relatively rarely in its training set. So it's not trained on. But if you asked it to write a program to multiply two numbers, it would get it right. So it has that sort of, it doesn't have that ability, or it didn't at that stage have that ability to do the reasoning and do the calculations. So you could ask it logic questions and it would not be able to do them. You could give it examples of them, and I still don't think it would be able to do them consistently well in the way that you're suggesting. What I'm hearing now about GPT, whatever number we're up to, is it 5 or 6? I can't remember. That's coming out, is that they've added an ability for it to do some reasoning. Now that depends what that means. I don't know what that means. But if it means that you could explain something to it in the way that you're saying, and it would understand that and be able to then use it, then maybe they have cracked it. But I have no idea how they've done it, to be honest.
And if I can just follow up a little bit. So I can see that advances in the ability for it to do reasoning would certainly help. But that ability to reason will presumably only work on the data set, which is in its kind of working memory that whatever you said, 32,000 characters or whatever. And that would always be kind of finite. But there seems to be something fundamentally different from that, between that and the ability to sort of like go back and change your whole intuitive understanding, the data which is actually in the weights as it were.
Yeah. No, I understand what you're saying, and honestly, I don't know what the answer is to that, other than, I mean, I think that we're moving to a situation where you have to, if you're going to do something like that, you'd have to understand, those long list of numbers, those vectors. You'd have to understand what those were corresponding to in language, and if you could do that well enough, you might be able to then have ways in which its output, which is essentially a long list of those numbers, relates to another output, which is a long list of numbers, and then you could perhaps do something with that. But I don't know if that's happening now or not. But it's certainly, yeah, you've picked up on a very challenging aspect. Thank you.
I'll take one from online now. This is Phil D. Hall.
Phil.
And his question is, where should we be focused on the basis of controls, governance, and legal positioning internationally? Where should that?
Thanks, Phil.
By talking with those that don't.
As you saw, it's difficult because these models currently in their current state are not guaranteed to produce acceptable outputs. And if you're a commercial organization, or if you're in a public service or health service or whatever it is, and you're applying this to people who don't understand the technology, and it says something to them that's harmful, they'll not be able to kind of understand how that output was generated and how to evaluate it. And so there is real risk there. I know that this is a bit of a waffly answer, but I know that the EU is trying to regulate all of this, especially in areas where there are people, vulnerabilities and ethical challenges. And they're stuck at the moment. And they're stuck on the fact that 3 member states of the Union do not want to put regulation on generative AI because they don't want to stop the innovation. It's always a balance between innovation and legislation, and I'm not well enough qualified to say which direction we should land in, but we should certainly be focusing our efforts on, the ethical consequences of, I mean, nobody thought about it. OpenAI I suspect, did not do a risk assessment on ChatGPT when they released it to the whole world. Right? They didn't really think about, well, what happens if this misleads somebody or causes somebody to harm themselves, which it has. So I think we do need to focus on that. But the people who are in the place of making legislation are trying to balance different things, and I suspect that the commercial interests might hold sway in many situations. It's a bit of a waffly answer. Sorry, Phil.
Next one from the audience.
I'm just going to comment that
Can you use the microphone, please, so the people online can hear the question?
I was just going to comment about the announcement of Google Gemini today, very timely for your talk, I thought.
Yes.
But I want to ask, what is the chances of deep knowledge being introduced to work with LLMs? It seems like the first model you showed of the historical work was probably using more deep knowledge rather than just pure language assessment.
Yes.
And we possibly regressed a little bit in terms of the accuracy with LLMs, despite their, it's the old garbage in, garbage out story. So I was wondering whether there's any opportunity, do you foresee a situation where LLMs will be combined with deeper knowledge models?
Absolutely, and I think that is definitely the way to go. I mean, I would be looking in particular at graph models, knowledge graphs as a way forward, because you can encode those in sort of machine learning contexts. But in order to do that, you have to be able to relate the output of the ChatGPT, say, with an item of explicit knowledge. which comes to the problem of, in that graph, those little dots, how do they relate to an explicit representation of knowledge? I think it's doable, and I think it's a really interesting research problem. But it feels like we're not there yet. But if we can do that, if we can figure out a translation, which I'm sure we can, so that we can map those vectors onto statements of knowledge, you can then take advantage of the fact that your vector space, your embedding space, statements that are close to that will express similar knowledge to that. So, and then you can use that space to do some kind of reasoning. Statements in this part of the space relate to statements in that part of the space in a particular way. So I think that it's doable. I don't know if anybody's doing it, but it certainly would be an interesting and challenging problem to solve. Thank you.
At the end of your talk, you were talking specifically about the computational energy cost of using just training GPTs in general. And one thing that comes to mind with comparing the output and energy usage of the human brain versus a computer is how efficient our computations are, just physically speaking. You can optimize those neural networks and spiking neural networks, but they do, that's very cool. But do you know if there's any theoretical limits that you're going to hit where at a certain point, just using silicone is going to hit a base limit no matter how long you try?
That's a good question. I knew you'd ask a question like this. I don't know of any limits. I mean, are you talking about neuromorphic hardware, that kind of solution? They do tend to be, so neuromorphic hardware is where you take, those spiking models and you actually build chips that reproduce that kind of computation rather than you would have a normal computer that's used for artificial neural networks. But your neuromorphic chips are much more optimized to produce these spike signals and connect with many thousands of other neurons and so on. And the limitations tend to be still on how many of those you can fit on a chip and how many synapses they can have to connect to other neurons. But I don't see that as a hard limit. I think it just needs a bit more ingenuity. For me, I think that the challenge is not so much just taking that basic thing that I showed you and placing it on a chip. It's thinking a bit more, it's understanding a bit more how neurons in the brain actually process information. And those neuromorphic chips have basically one way of doing it, that you encode one simple sort of spiking neuron algorithm that you put in all the little neurons to make them work. But the brain is so much richer than that in how it processes information, and we really, that to me is where the biggest gains are to be, rather than producing chips that are more efficient and bigger, but basically use the same kind of architecture as the original artificial neural networks. So I think that's the way to go, is to really understand more about what's happening in the biological context.
Take another question from online from Jera Mara. What are the opportunities for small startups to develop generative AI products, considering the massive financial barriers to create models, etc.?
Well, it's happening. Some of them are doing it. It is possible to do it. You can get scaled down versions of the models where they just, instead of using 64-bit accuracy of numbers, you just use 4-bit, and it works pretty well. Language models work pretty well, and you can run on low-cost devices. And there are some organizations that are able to train reasonably well-performing language models on a smaller data, very bespoke data sets. So very often it's, you want to apply this to a particular area like healthcare or something like that, and you have a very sort of set amount of knowledge you want the system to learn. And so, you know, that you can actually develop some reasonable models, but if you want very high level performance, GPT level performance, I don't know if that is yet accessible. So it does, so smaller models are possible. It's just that they don't perform so well.
Any more questions from the audience here? Go back here. Unless there was someone. No, that's it.
So do you think that in 100 years' time, do you think we'll be still using silicon-based? People go down to the wet spot that can grow. And I guess, would there be any moral?
There would indeed be a lot of moral implications. People are trying to do that already. I used to do some evaluating for and reviewing for the EU, and there was a project that used to grow neurons to control a robot cart that trundled across the floor, and I had huge sort of ethical concerns about that. But I suspect it will happen. I suspect that it's the way to go, because I think, you know, as we're able to control the biology and connect it with the technology. I mean, there was a time where it was really, really difficult to connect an electrode to a brain cell, a neuron cell, and it would essentially avoid it. If you put something that could drain the voltage of the cell on it, why would it want to do that? I mean, that's costing it, so it kind of, you know, moves away from it. But that's been overcome now, and they can do that pretty well. The thing is, what is the gain, and do we understand the biology well enough? And maybe in 100 years' time we will, I guess, understand the biology well enough. I don't know how to answer it, because I do have such big concerns about it, because we're basically growing brains in biology and connecting them to machines potentially. And where will that lead? I don't know. It's a bit science fiction-y, isn't it?
Bet, you know, if you had £100 to bet on one or the other, you know, in 100 years' time, you know.
I think somebody will do it. I think somebody will do it. I think we'll reach a point where actually we understand enough about the biology to build meaningful and functioning and efficient living networks. But I wouldn't want to be on the ethics board for that, because I think that's just a minefield. I don't know.
You should be for that.
Maybe I should be. Yeah, I don't want to see it happen, but I can see that somebody will do it and make it work.
I'll ask another one from online. This is from Ben Buckvale. Definitely the energy usage of AI is a real concern as we become ever more dependent on it. So it's interesting to hear of more efficient techniques being researched. My understanding is we're yet to exploit the full performance benefits of using GPUs to assist with training. In the research you're doing with these more efficient approaches to training, are you able to exploit the GPU just as well as standard training approaches?
Yes, you can. Yeah, so you can. I mean, there are libraries that you can use that will take advantage of GPUs to optimize performance. You know, program in Python, and there's a lovely library called Brian2. I don't know why it's called Brian2, but there we go. Which helps you to build biological models of neurons very nicely and do experiments with them, and it's great. And you can optimize that, you know, using GPUs. I think that's useful for small scale, but we will need something a bit more ambitious when we get to doing large scale networks of neural. Well, there are. I mean, the Human Brain Project is a European funded project that's been running for 10 years now, I think. And has generated a lot of hardware and stuff related to this kind of thing. So, yeah, I don't know. Let's leave it there.
I'm curious that you're hesitant to produce new brains to do the work. But in 100 years, we might use existing human brains to do the work. So we don't need to build any more brains. And we've got a lot of capacity, but we don't use them.
Yeah, I agree. Well, yes, I mean, I'm hoping that human brains will still be useful in 100 years' time. But I think the sort of the original question was, can we grow brains? You know, take some stem cells and start developing neurons and connecting them together, and we can, you know, I could see it happening. I could see that that would happen. I could see that it might be better than anything we can create artificially. It's just whether we really want to do it or not. That's the thing that is. Yeah, I'm not an ethicist, so I'm not really equipped to be able to answer that question, other than it just doesn't quite feel right because you're creating a living thing and then you're, yeah.
Be self-aware.
Yeah, what happens if, yeah, I don't know. What's the difference?
Can we not have if we have a discussion within the audience, it's interesting for the people in the room, but people online won't be able to hear any word you're saying. So I have to impose a little bit of structure on that. I'll take a question from online, which is from Neil P. How do you see quantum computing helping reduce the training timescales, etc.?
Yeah, so I mean, I do see that. That's not an area that I looked at personally, but I've been in the room when it's been talked about. So yeah, we should use it if we can use it to optimize and reduce energy and all that kind of stuff. I think quantum computing has definitely got a role to play here because we've got massive search spaces, and quantum computing provides us with solutions to traverse those with greater efficiency. So we should definitely use it, but it's not something that I know a great deal about.
Right.
Do you see an evolution of the current approach leading to understanding? Or do we need a completely different approach to get if you like, a truly intelligent artificial machine or whatever?
Yeah, you'd have to define understanding. What do you mean by understanding, really, to be able to answer that question well? Are you talking about consciousness, or?
Well, I was thinking you said when you were talking about your very first
Yeah.
steps 15 years ago
Yeah.
or so, that there was no empathy or understanding of what was being said.
Yeah.
And the response.
So yeah, so I mean, so in the original Avatar in Samuela, we tried to simulate emotion. We tried to estimate the emotional state of the user. That to me doesn't mean understanding. It just means that architecture was more understandable to a human being because we can look inside it and see what it's doing. Whereas, you know, with neural networks and GPT, you know, it's incredibly difficult to understand what it's actually doing and where the information content is going, because it's just spread everywhere and then comes back together at the end. So we're really getting onto the sort of philosophy end of things. You know, when you talk about understanding, does the machine understand? Well, you can ask it questions and it can answer them pretty well. I mean, Turing would have accepted that kind of test, wouldn't he? But does it understand? I would say without consciousness, no. But that's my personal view, and yeah, I'm not a philosopher either.
Just going to take one more question from online, and then I think we're going to have to wrap up for this evening. But this is a very short and simple question.
Oh, good.
I think you've answered. Well, it's not actually. It's not simple. It's very short, but I think you partly answered it already. But the question is it safe? By which I think the author means generative AI.
Generative AI.
And I would add to that, and if it's not, who should be governing it?
Oh gosh, that's such a good question. Is it safe? In my view, no. It's not totally safe. Who should be governing it? Well, the large corporates want to govern themselves. Obviously, they want to do self-regulation because that they can then kind of set it up so that they might still keep their profits. Some governments, so as I was saying, the EU wants to bring down some tight regulations on it, which it will, I'm sure it will introduce. The US is trying to be a bit more flexible and creative about it. The UK is trying to steer a course in the middle. I don't know. I think at some point there's going to have to be some mix of governmental regulation and oversight and corporate oversight and responsibility. How that's done, I have no idea. I mean, I'm not a legal expert, so I wouldn't know how to set that up. But it seems to me that if we allow the companies just to define their own ethical regulations and contexts, and we're probably asking for trouble. But we also don't want to completely damp down the creative and the innovative application of the technology through these corporates. So I would say that there has to be, both parties have to be involved.
Great, thank you very much. So thank you very much for your answering all of those questions. Thank you to the audience both here and online for putting the questions. But I think the main thanks again are to you, Nigel, and many thanks for this afternoon.
Thank you.
So,